In this session, we shall consider the closed loop and open loop configurations of an op-amp. First of all, let us start with open loop configurations of an op-amp. The term open loop indicates that no connection exists between input and output directly or via another network. That is, feedback is open. There are three types of open loop configurations. 1. Inverting amplifier. 2. Non-inverting amplifier. 3. Differential amplifier. First of all, let us take up inverting amplifier. As shown in figure, the signal source is connected to the inverting terminal of an op-amp and non-inverting terminal is grounded. RS, that resistance, represents the source resistance. RL indicates load resistance. Output is taken across this load resistance. This configuration is called inverting amplifier because the positive voltage applied at the inverting terminal of the op-amp produces inverted output. That is, there will be a 180 degrees phase shift between output and input. That is, if positive voltage is applied at the input, we will get negative voltage at the output. That will be with an amplification. Now, let us calculate the output voltage. As shown in figure, V1, that is the voltage at non-inverting terminal, equal to 0 because non-inverting terminal is grounded. V2 is the voltage at the inverting terminal, and to the inverting terminal, source voltage Vs is connected. If we neglect that source resistance Rs, then V2 equal to Vs, and the output voltage is given by the gain, open loop gain AOL times VID, where VID is the differential input voltage. That is, it indicates the difference between two input voltages V1 and V2. Therefore, VID equal to V1 minus V2, that equal to minus V2. Substituting V2 equal to Vs, we will get VID equal to minus Vs. Therefore, V0 equal to minus AOL into Vs. That is, output voltage is 180 degrees out of phase with input voltage Vs, and the input voltage Vs is amplified by a gain factor of open loop gain AOL. The second type of open loop configuration is non-inverting amplifier. Here, in this configuration, the signal source is connected to the non-inverting terminal of the amplifier and inverting terminal is grounded. Output is taken across the load resistance. This configuration is called non-inverting amplifier because the positive voltage applied at the non-inverting input terminal produces the positive output voltage. That is, there is no inversion between output and input. Therefore, we are getting non-inverted output, and hence this amplifier is called non-inverting amplifier. As shown in figure, the inverting terminal is grounded to the non-inverting terminal, which is indicated by positive sign, is connected to the signal source, and output voltage is taken across RL, and its output voltage is calculated as follows. The non-inverting terminal input voltage V1 equal to Vs, inverting terminal input voltage V2 equal to 0 because inverting terminal is grounded, and hence input differential voltage VID equal to V1 minus V2 equal to V1 that equal to Vs, and hence V0 equal to AOL VID equal to AOL Vs. Therefore, output is an amplified form of input, but there is no phase shift of 180 degrees. That is, output is non-inverted form of input voltage. The third type of open loop configuration is differential amplifier. Here, two input signals are used and they are connected to inverting input terminal as well as non-inverting input terminal, and hence if V1 is the voltage appearing at the terminal inverting input terminal as shown in figure, the voltage appearing at non-inverting terminal is V1 equal to Vs1 and the voltage appearing at inverting terminal is V2 equal to Vs2. Therefore, the input differential voltage VID equal to V1 minus V2, and hence output voltage is equal to VOL VID, that is V0 equal to open loop gain AOL into Vs1 minus Vs2, that is output voltage is amplified form of the difference between input signals, and hence this differential amplifier is also called difference amplifier. In the above three open loop configurations, we have derived the expressions for output voltage, but we know that open loop gain of an op amp is very high. It is of the order of 1 lakh. Therefore, the linear operation region is very small in the open loop case, but we require the large linear operation, that is output follows the derived expressions only in the linear region. When it reaches saturation level, these output equations are not valid. So, in order to get the large linear region of operation, the gain should be reduced. To reduce the gain to reasonable value, we have to apply a feedback. When a small part of the output signal is coupled to input, the amplifier is called feedback amplifier or closed loop amplifier. Types of feedback. There are two types of feedbacks. 1. Positive feedback. 2. Negative feedback. In the positive feedback, the feedback signal is in phase with the input signal and it is used in oscillator circuits because it increases the output signal value. Negative feedback. In negative feedback, the feedback signal is 180 degrees out of phase with the input signal and it is used in amplifiers where reduction in gain is required to get the stability of the gain, and it is also having several other advantages. So, we require negative feedback to reduce the gain of an op amp and to operate it in the linear region. Classification of negative feedback circuits. There are 4 types of configurations in the negative feedback. 1. Voltage series feedback amplifier. 2. Voltage shunt feedback amplifier. 3. Current series feedback amplifier. 4. Current shunt feedback amplifier. Voltage series feedback amplifier is called non-inverting amplifier with feedback or closed loop non-inverting amplifier or simply non-inverting amplifier. Voltage shunt feedback is called inverting amplifier with feedback or closed loop inverting amplifier or simply inverting op amp or inverting amplifier. The block diagrams for voltage series feedback amplifier and voltage shunt feedback amplifier are shown in the following figures. The current series and current shunt configurations are not used with op amp. because the current gain is not defined with a differential amplifier. Classification of negative feedback op-amp circuits. Basically, there are three types of negative feedback op-amp circuits. 1. Inverting op-amp. 2. Non-inverting op-amp. 3. Differential op-amp. Now, let us analyze each type of these feedback networks. First of all, using ideal op-amp, and then let us use the practical op-amp. Inverting op-amp. As mentioned earlier, the signal source is connected to the inverting terminal of the op-amp and non-inverting terminal is grounded. Here, as shown in figure, there are two resistors used in the circuit. Resistor 1 is connected from inverting terminal to the signal source and resistor R2 is connected from inverting terminal to the output terminal. The resistor R2 is the feedback resistance and the voltage coming from output terminal to the input signal source terminal, inverting terminal 2, depends on the values of both R1 and R2. The ideal op-amp characteristics are its open loop gain is infinity, input resistance is infinity and output resistance is 0. By using these characteristics, let us derive the expressions for closed loop gain, input resistance with feedback, output resistance with feedback. As shown in figure 1b, the op-amp is replaced by its equivalent circuit. The input resistance is infinity for ideal op-amp, so it is shown as open circuit across the terminals 1 and 2. Output resistance is 0, so it is shown as a short at the output terminal. And control voltage is AOL VID, where VID is the differential input voltage. Let the current I is flowing through the resistance R1 due to the signal source Vs. The same current flows through R2. This is because the input resistance is Ri equal to infinity and hence the base voltages I1 and I2 are equal to 0. Therefore, the same current I will flow through R2 and VID equal to V1 minus V2, and here V1 is the terminal voltage at non-inverting terminal 1 and that is 0 because it is grounded. Therefore, V1 minus V2 equal to 0, where V1 equal to 0 leads to V2 equal to 0, that is V1 equal to V2 equal to 0. This circuit is called inverting amplifier because the positive voltage Vs applied at the inverting terminal produces 180 degrees out of phase signal at the output. That is, output is an inverted form of input. Let us prove it with mathematical expression by deriving an expression for closed loop gain. Closed loop gain, it is denoted by AV. Since I1 equal to I2 equal to 0, the current I through R1 also passes through R2. As VID equal to 0, I equal to Vs by R1, that equal to minus V0 by R1. Therefore, voltage gain defined as the ratio of output voltage to input voltage, that is V0 by Vs, is equal to minus R2 by R1. And this expression indicates that V0 equal to minus R2 by R1 times Vs. Therefore, there is a 180 degrees phase shift between output and input, and its gain's magnitude is R2 by R1 and it is less than infinity, and hence this circuit provides a reduction in the gain and also provides 180 degrees phase shift between input and output. An electrical ground is one which is having 0 voltage and which can sink infinite current. This is the ground usually we come across in all electrical circuits, but there is a special ground known as virtual ground connected with op amps. A ground is said to be virtual if it has 0 voltage and 0 current. In the ideal inverting op amp, since VID equal to V1 minus V2 equal to 0, we got V2 equal to 0 because V1 equal to 0 due to the ground at the non-inverting terminal. Therefore, the voltage at the inverting terminal junction point 2 is 0. At the same time, because of the ideal nature of the op amp, I1 equal to I2 equal to 0. Therefore, the inverting terminal is having both voltage equal to 0 and current equal to 0, and hence the point at the inverting terminal acts as a virtual ground. Due to this virtual ground, the current flowing through the resistance R1 is equal to the current flowing through the resistance R2. Now, let us calculate the input resistance with feedback. And this input resistance is defined as the equivalent resistance present at the input signal source, that is the resistance seen by the input signal source with the other terminal being grounded. The input resistance with feedback is represented by RIF. From figure 1b, we get RIF equal to the ratio of input voltage Vs to the current flowing through the resistor R1I. Therefore, input resistance with feedback is equal to R1. The output resistance is defined as the equivalent resistance present at the output terminal. Let us calculate the output resistance present in the case of inverting op amp. Output resistance with feedback is represented by R suffix OF. From figure 1b, we get R with feedback is equal to 0, that is ROF equal to 0, because we are measuring the resistance across the control signal source AOL VID, which is having 0 resistance. The real op amp characteristics certainly deviate with the characteristics of the ideal op amp. So, we have to go through the analysis of the real op amp circuits. So, let us start the analysis of inverting amplifier with real op amp. Practical inverting op amp. For real op amp, that is practical op amp, open loop gain is less than infinity, input resistance Ri is not equal to infinity, it is always less than infinity, and output resistance R0 is not equal to 0, that is it is always greater than 0. That is finite amount of output resistance exists in the case of practical op amp. Now, as shown in figure, practical op amp equivalent circuit is consisting of input resistance Ri, output resistance R0 and control source AOL VID. R1 is connected at the inverting input terminal and R2 is connected between output and input. The equivalent circuit of figure 2b can be redrawn as shown in figure 2c. We can replace the network consisting of Vs, R1 and Ri by its Thevenin equivalent circuit. If the Thevenin equivalent resistance of this simple network is R1 prime and its Thevenin voltage is Vs prime, then the equivalent circuit of figure 2c is as shown in figure 2d, where Vs prime is equal to Vs Ri by R1 plus Ri, R1 prime is equal to R1 Ri by R1 plus Ri. Now let us determine the expressions for closed loop voltage gain, input resistance with feedback, output resistance with feedback connected to the practical inverting op amp. Closed loop voltage gain. From figure 2D, we get the differential input voltage VID equal to minus of IR2 plus V0, but V0 equal to IR0 plus AOL VID. Applying KVL to the input loop, we get Vs prime equal to I times R1 prime plus R2 plus R0 plus AOL VID. Solving the equations 1 to 3, we get V0 by Vs prime equal to minus AOL R2 plus R0 by R0 plus R2 plus 1 plus AOL into R1 prime. Let this be equation 4. Since Ri is very greater than R1, Ri plus R1 is approximately equal to Ri. Vs prime equal to Vs Ri by R1 plus Ri, that is approximately equal to Vs. R1 prime equal to Ri R1 by Ri plus R1, that is approximately equal to R1. Using these approximations in equation 4, we have voltage gain in closed loop is equal to V0 by Vs equal to minus AOL R2 plus R0 by R2 plus R0 plus R1 times 1 plus AOL. Since AOL is very greater than 1, otherwise in our circuit, if the closed loop gain is very greater than 1, then AOL R1 is very greater than R2 plus R0 and AOL R2 is very greater than R0. With these approximations, we get AV equal to minus AOL R2 by R2 plus R0 plus AOL R1, which is approximately equal to minus R2 by R1. Neglecting R0, the closed loop gain becomes AOL R2 by R2 plus R1 into 1 plus AOL. The closed loop gain derived expression is minus R2 by R1. So, by selecting proper values for the resistances R1 and R2, we can get the desired gain value. If we want to get the closed loop gain equal to 10, then select R1 equal to 10 kilo ohms and R2 equal to 100 kilo ohms, which gives minus R2 by R1 equal to minus 10. Now let us take up input resistance with feedback. The input resistance with feedback is the resistance seen by the input signal source by connecting the other terminal to ground. Since Vs prime is approximately equal to Vs and R1 prime is approximately equal to R1, the current flowing through the loop with RL equal to infinity is given by I equal to Vs minus AOL VID by R1 plus R2 plus R0 and VID equal to IR1 minus Vs. Substituting equation 8 in 7 and simplifying, we get input resistance with feedback RIF equal to Vs by I equal to R1 plus R2 plus R0 by 1 plus AOL. In this session, we started with open loop configurations and we have derived the expressions for output voltage in case of the three types of open loop configurations. One, inverting open loop configuration, and second one non-inverting amplifier, and third one differential amplifier. And then we took up the topic closed loop configurations. In closed loop configurations, we started with the inverting op amp. In that inverting op amp, first of all, we considered the ideal case and we have derived the expressions for closed loop gain, input resistance with feedback, output resistance with feedback for that ideal op amp circuit. Then we took up the topic practical inverting op amp. For that practical inverting op amp, we have derived the expression for closed loop gain and input resistance. In the next session, we shall consider the topic of derivation for output resistance and other closed loop configurations.